Hello students. So in this lecture we are going to discuss about the hydrogen atom problem. Okay. Uh, it is also referred as one electron atom problem. So in this we all know the structure of hydrogen atom problem. So it has one electron and one proton. So electron is orbiting around the nucleus, and in the nucleus there is one proton. So so there is an electron which is orbiting. There is a nucleus, okay, and inside this nucleus there is one proton, okay, and this electron is revolving around this nucleus. So you know that it is since it is an electron and this is a proton, so there will be a coulombic attraction. So there is a coulombic potential. So in this coulombic potential we have this is represented as V as a function of R, where R is basically the magnitude of distance between both of this, and this is written as minus Z E square by R. For hydrogen, Z is equal to 1, and since the charge of a proton and electron are equal, just a negative sign is there in electron, so there is a negative sign here. So it is an attractive force, and this is generally known as the central force problem also. Okay, since the force is always directed towards the center, it is similar to the Kepler problem or any other problem where a planet is revolving around the Earth, and the force of the planet is always towards the center. Okay, planet is revolving around the Earth is revolving around the sun. Okay, so this all come under the category of central forces, and in central forces the potential is always inversely proportional to 1 by r. Okay, whether you take the Kepler problem or with this hydrogen atom problem or any other problem. So this is your potential, and now let me write the let me write the mass of electron as m1, the mass of the proton is m2. Okay, and let me write the Hamiltonian for the problem. So Hamiltonian for the problem will be the summation of the total kinetic energy of the system plus the total potential energy of the system. So kinetic energy here will be due to two factors. One will be due to this electron and one will be due to this proton, or you can say the nucleus. So I will write H is equal to P1 square by 2m1, okay, then P2 square by 2 m2, and plus the potential energy here is only due to this Coulombic potential energy which is between the electron and the proton, nothing else. So I will write V, which is a function of magnitude of r1 minus r2. Okay, so this is the kinetic energy due to electron, this is the kinetic energy due to uh, proton, or you can say nucleus also. Okay, and this is the potential energy of the due to the Coulomb force. So we are having these terms now in three dimensions. Okay, we are all aware that P, okay, will be equal to minus IH cross, okay, del by del x plus del by del y plus del by del z. Okay, so this is the expression of the momentum operator in three dimensions. So here there are two momentum operators, one is for electron and one is for proton. So here I will write, okay, since it is p square, so it will be minus h cut square del by del x1 square plus del square by del y1 square plus del square by del z1 square. Okay, into psi, okay, which is a function of r1 comma r2 minus h cut square by 2. Okay, I forgot to write this term here. M2, okay, del square by del x2 square plus del square by del y2 square plus del square by del z2 square, okay, into psi, okay, plus the potential term which is a function of magnitude of r1 minus r2 into psi is equal to e into psi is equal to function of r1 comma r2. Okay. So r and r1 is basically nothing but x1 y1 z1 and r2 is nothing but x2 y2 z2. Okay. So I have this thing with me. This differential equation is with me right now. And what is our standard practice? Our standard practice is basically that we do the separation of variables and let us separate all the terms and solve it. Okay. So basically our tendency is to write psi of r1 comma r2 is equal to psi of r1 into psi of r2, and let us do the separation of variable and solve this term. Now this thing will work here very fine. Here also it will work very fine. Here also it will work fine. But here, okay, since the potential is a function of R1 and R2 both, so it is not possible to do a separation of variable in this potential term. And if it cannot be done here, then we cannot do anywhere else also. So it is not possible. So this thing cannot be done right now. Okay. So the separation of variable right now is not possible. So what to do now? Now in this existing form, this thing is not possible. Okay. And we don't have any other way also, because see, in this differential equation we are having 6 differentials, that too of second order, and now it cannot be solved using okay, any other method. So right now we have to do some other technique, and that is generally known as coordinate transformation. Okay. Coordinate transformation is very helpful tool, okay, in such kind of problems. So what we are doing is we are introducing new coordinates. The first coordinate is relative coordinate, okay, which is denoted with r vector, and this is nothing but the difference of r1 minus r2. Okay, so basically what it means, x is equal to x1 minus x2, y is equal to y1 minus y2, z is equal to z1 minus z2. Okay, and the other coordinate which I am introducing is actually the center of mass coordinate. It is denoted with capital R vector, and it is generally written as m1 r1 vector plus m2 r2 vector divided by m1 plus m2. Okay, so what it means, that capital X is equal to m1 x1 plus m2 x2 divided by m1 plus m2. Similarly, you can write the expression for capital Y, and you can write the expression for capital Z. Okay, so we have now the values of x and capital X. Okay, so if x can be written in terms of x1 and x2, okay, you can see that x is written in terms of x1 and x2, and capital X is written in terms of uh, small x1 and x2. Here you can see. So from both of these expressions, I can write small x1 as a expression of, as a function of small x and capital X, and this x2 also can be written as a function of small x and capital X. Okay, so this is what I am going to do. So the wave function, which was initially the function of r1 vector comma r2 vector, is now transformed as a function of r vector and capital R vector. Okay, so this is what I am actually doing. So now we have, so this is done. Okay, but now I have to write this differentials also in terms of small x and capital X. They are right now in terms of this thing. So if I want to calculate del square psi by del x1 square, then how will I do it? Okay, in terms of small x and capital X. So first of all, let me find the values of del psi by del x1. Okay, so since you know that psi is a function of small r and capital R, so right now since we are talking in terms of x1, so here I can write psi is a function of small x and capital X. So what will happen? I can write del psi by del small x into del small x by del x1 plus del psi by del capital X into del capital X by del x1. Okay, so I have the value of I have to calculate the value of del x by del x1. Okay, so you can find that del x by del x1 can be calculated from here. Okay, and the value will be equal to 1, and the other value which I have to calculate is, so this is equal to 1, and del x by del x1 will be equal to, if you see here, then it will be equal to m1 upon m1 plus m2. Okay, so it is equal to, okay, m1 upon m1 plus m2. So these two values can be substituted here. So I will get del psi by del x1 is equal to del psi by del x plus m1 upon m1 plus m2, and this will be del psi by del capital X. So I have written del psi by del x1 in terms of only small x and capital X. Okay, but I have to calculate d square psi by dx1 square. So what I will do, I will take d by dx1 of d psi by dx1. So what will happen here? Okay, now see it done. I have to first calculate uh, this thing. So it will be equal to del by del x into just a minute, del x, sorry, del x by del x1, okay, into del psi by del x, okay, plus, okay, I am talking about first term right now. So it will be d by dx, okay, into dx by dx1 and into del psi by del x. Okay, so this is the first term right now. Okay, similarly you have to do for the second term. So first of all, what I will do, I will take this term common, m1 upon m1 plus m2. Okay, and I have to take this term, so I will be writing, okay, del by del x into del x by del x1, okay, into del psi by del capital X, okay, plus del by del capital X into del capital X by del x1 into del psi by del capital X. Okay, so this is the entire expression. So now you again have the value of del x by del x1 and del capital X by del capital 1. Okay, so you have to substitute all these values again, and you will be getting this is equal to, okay, so this is nothing but del square psi by del x1 square, and this will be equal to d square psi by del x square minus del square psi by del capital X into small x, okay, into 2m1 upon m1 plus m2, sorry, 2m2 will be here, okay, plus m2 upon m1 plus m2 the square d square psi by d x square. Okay, so this will be expression of del x del square psi by del x square, and you can see that this entire expression is in terms of small x and capital X. Okay, so we have removed the dependence of x1 from here, and you can similarly calculate the value of no, here it will be m1 itself. Okay, so okay. And similarly you will be having d squares by dx2 square, and this will be equal to del square psi by del x square minus del square psi by del x into, this is capital X and this is small x. Here it will be 2m2 divided by m1 plus m2, okay, plus m2 by m1 plus m2 the square d square psi by d x square. Okay, so this will be the expression for this, and now what you have to do is you have to actually take the, so here it was del x square by del x1 square, and here you are having x2 square, so you have to write, if you club both these terms then you will be having, okay, minus h cut square by 2m1 del square psi by del x1 square minus h cut square by 2 m2 del square psi by del x2 square. Okay, so what this term will be equal to? Okay, this will be equal to minus h cut square by 2 1 upon m1 plus 1 upon m2 into d square psi by dx square minus m1 plus m2 divided by 2 m1 plus m2 square, okay, into h cut square del square psi by del, okay, capital X square. Okay, so in this expression, if you see, then 1 upon m1 plus 1 upon m2 can be written as reduced mass. Mu, which is equal to 1 upon m1 plus 1 upon m2, and here we can remove just two terms, and this is m1 plus m2. I am writing this as a capital mass m, capital M, okay, which is summation of both masses. So I can write now, okay, sorry, it is 1 by mu, so 1 by mu is equal to 1 upon m1 plus 1 upon m2, and mu is the reduced mass. Okay, so this will be equal to minus h squared square by 2 mu minus h squared square by 2 capital M del square psi by del capital X square. Okay, so this was the term which I have done for x1 and x2. You can do it for similar procedure for y and z also, and they will give you exactly same terms. Okay, so this will be written as, okay, so the Schrödinger equation, okay, in terms of capital small x and capital X and small y and capital Y, all those terms can be written as minus h cut square by 2 mu. Okay, so I have this term, so I will be having exactly same terms for y and z also, so I will just add them. D square psi by d y square, d square psi by d z square minus h cut square by 2 capital M del square by del capital X square plus del square by del capital Y square plus del square by del capital Z square, okay, into psi. Okay, here also I can take psi common. I should take it, I think, equal to, okay, plus v, which is a function of r1 minus r2, and r1 minus r2 is nothing but, okay, mod of r vector, okay, equal to into psi into e into psi, and psi is a function of small r and capital R. Okay, psi is a function of small r and capital R. Now here separation of variables can be done. Why? Because v is now function of only small r. Okay, psi is a function of small r and capital. So now the separation of variables can be done. So now I can write psi, okay, as function of r vector and capital R vector as capital psi, which is a function of r vector, and capital phi, which is a function of capital R vector. Okay, so you will be getting minus h cut square by 2 mu into 1 by capital psi, okay, del square by del x square, del square by del y square plus del square by del z square into psi plus b of r, since it is just a magnitude, okay, minus, okay, h cut square by 2 m 1 by 5. What I have done is I divided the entire term by capital psi, okay, multiplied the entire term with capital psi and phi, okay, after substituting this. So you will be getting del square by del x square, del square by del y square, and del square by del z, capital Z, this is, into phi, okay, and this is equal to e, okay. So I am having this term, okay. Now you can see that this is entirely, okay, so psi is a function of r, and psi is a function of r. So this term is entirely the function of r, and this is entirely the function of capital R. Okay, so this corresponding Hamiltonian will give you the energy corresponding to the center of mass. Okay, and this will be giving you about relative coordinates, but this is nothing but this will give you the information about internal motion of hydrogen atom. Okay, so the total energy will be the energy due to this term. So you calculate the eigenvalue of this term. This will give you energy due to the internal motion of hydrogen atom, and this will be giving you the energy due to the center of mass motion. So COM, and this is nothing but equal to E total. So you can take first of all the center of mass term, and this is equal to minus h cut square by 2 into capital M into 1 by capital phi, which is a function of capital R, and d square by d x square plus d square by d capital Y square, d square by d capital Z square into phi, and this is the energy corresponding to the center of mass. Okay, so this is capital X, so it is del square by del capital X square, del square by del capital Y square, del square by del capital Z square, okay, into phi, okay, and equal to E center of mass, okay, by h cut square, and this is into 2m minus 2me by h cut square, okay, and into phi, which is a function of capital R. So I am having these things. So I can write this term, okay, as p square. Okay, so 2me can be written as p square. So I will be writing d square by del capital X square plus del square by del capital Y square plus del square by del capital Z square into phi is equal to minus, okay, p square by h cut square into phi, okay, and from this you can calculate phi, which is a function of capital R, equal to some constant k to the power I p dot capital R by h cross, and this is equal to, sorry, not, so this is equal to phi. So we have solved it for phi, and you can see this is exactly similar to the wave function of a free particle. Okay? So it looks like a free particle. Okay, so the center of mass, okay, moves as a free particle with energy, okay, p square by 2m, where m is equal to m1 plus m2, okay, m is equal to m1 plus m2. So this was about the center of mass particle. This is not very important. The most important thing is about the internal motion of hydrogen atom, okay. So now let us talk about the internal motion term, which is actually this term, okay. So here if you take this part, then it is equal to minus h cut square by 2 mu. Mu is the reduced mass, 1 by capital psi d square by del x square, del square by del y square plus del square by del z square into psi plus v of r and equal to e. So this is the term which is giving you information about the internal motion of the particle, and this can be written as, okay. So this is nothing but the Laplacian operator. So I can write this as the Laplacian operator del square psi, okay, plus 2 mu by h cut square into e minus v of r into psi of r is equal to 0. Okay, so now I have this term with me. Okay, and I have to solve this term. Now I have the Laplacian with me, and this is r coordinate. Okay, so what I will do is I will try to solve it in the spherical polar coordinate. Okay, so in spherical polar coordinate, the value of Laplacian you must be knowing from a mathematical physics course, and the Laplacian del square psi will be written as 1 by r square into del by del r of r square into del psi by del r plus 1 by r square 1 by sine theta del by del theta of sine theta del psi by del theta plus 1 by sine square theta into del square psi by del phi square. Okay, so this is the Laplacian operator in the spherical polar coordinates. Now you try to see this term. Okay. You should be familiar with this term, okay, from the angular momentum topic. Okay, let me write the L square operator when it operates on psi. It is equal to minus h cut square 1 by sine theta del by del theta sine theta del psi by del theta plus 1 by sine square theta to del square psi by del phi square. So if I have this with me, so you can see that this thing and this thing are same. Okay, so I can replace this thing with the L square operator. Why? Because I know that what are the wave functions of L square operator. Okay, so what I will do is I will write this entire term as L square by minus h square. Okay, so del square psi will now be written as 1 by r square del by del r r square del psi by del r, and instead of writing this term I will be writing minus L square psi into r square h cut square. Okay, so I have this thing with me. Now what I will do is I will substitute this value of Laplacian operator. So if I tell this as equation number 1 and this as equation number 2, so it means that I am substituting 2 in 1. So if I substitute 2 in 1, okay, then I will be having 1 by r square del by del r of r square del psi by del r minus L square psi upon r square h cut square plus 2 mu by h cut square e minus v of r into, okay, psi, okay, equal to 0. Okay. Now since we are in the spherical polar coordinates, so psi will be a function of r theta and phi, and I can write this as a function of r and r, and another function as function of theta and phi combined. Okay, so what will happen here now? It is 1 by r square. Okay, and y theta phi will come outside here, and I will be having del. Okay, now this partial derivatives can be replaced with total derivatives. So I will be having d by dr of r square dr by dr. R is a function of small r only, and plus I am just keeping this thing with me, 2 mu by h cut square e minus v of r, and psi is written as r of r into y of theta comma phi equal to L square. Okay, so L square will be operating on theta and phi coordinate only. R will be taken outside. So L square operating on y theta phi divided by r square h cut square. So now we know that when L square operates on y theta phi is nothing but okay a function of theta and phi, and you can take this as a spherical harmonic. So you can L into L plus 1 h cut square, okay, into y theta phi. Okay, so this is the eigenvalue of L square operator, and you can directly substitute here. So I will be having now y of theta phi by r square d by dr of r square 2 mu by h cut square e minus v of r, okay, r of r y of theta phi, and here I will be writing r as a function of r, okay, and y theta phi, okay, and now I have few constants with me, L into L plus 1 h cut square upon r square h cut square. So h cut square can cancel out, okay, and if you see this entire expression, then you can also cancel out this y theta phi also, or in different language if I say, if I substitute multiply entire equation with r square upon r of r and y of theta phi, okay, so if I multiply this, what I will be having, 1 upon r of r, okay, d by dr of r square del r by del r plus 2 mu by h cut square, okay, into r square e minus v of r, okay, is equal to L into L plus 1. Okay, so now I have this thing with me. So what I can do now, I can take this thing here. So 1 upon r of r d by dr r square dr by dr plus 2 mu r square by h cut square e minus v of r, and I am also clubbing this term in this bracket. So I will be having minus L into L plus 1 h cut square on 2 mu r square, and this is equal to 0. Okay, so if I again multiply this equation with r of r by r square, I will be having 1 by r, r square d by dr of r square del L. Okay, this is total derivative, not partial derivative, plus 2 mu by h cut square e minus v of r, okay, minus L into L plus 1 h cut square. Okay. So this is, you can see that this is totally radial dependent equation. Okay, so this is the radial part of the Schrödinger equation, and now you can do some more manipulation with this equation. So what I am doing is I am substituting r, which is a function of r, as u of r by small r. So if I do this, I will be having del r by del small r is equal to minus 1 by r square u of r plus 1 by r du by d. Okay. So d by dr of r square del r by del r. I am calculating this term. Okay. So I have to first of all multiply r square with this. So it will be negative of u of r, and it will be r into del u by del r. So it will be d by dr of negative of u of r plus r into du by dr. So this is equal to minus of del u by del r plus del u by del r plus r into del square u by del r square. Okay, so this both terms will cancel out. So I can write del by del r of r square to del r by del r as r into d square u by dr square. So what I will do is I will simply substitute this term here. So I will be having the equation in terms of u now. Okay. So I will be having now, therefore, 1 by r d square u by dr square plus 2 mu by h square square e minus v minus L into L plus 1 h square on 2 mu r square into r of r was there, so I can write now this as u of r by r equal to 0. Okay, so this equation has been now written in terms of this. We have taken this as the uh, transformation. So therefore, I will be having d square u by dr square. Okay, plus 2 mu by h cut square E minus V minus L into L plus 1 h cut square upon 2 mu r square, okay, into u of r. Okay. This is very important equation known as radial Schrödinger equation, and this is the main equation of this theory. Okay, so this is known as the radial Schrödinger equation, and not only hydrogen atom, but you can solve many problems using this equation. Okay, like you can solve hydrogen atom with this equation. You can solve the deuteron problem. Okay, you can solve the diatomic molecule. Okay, so you can solve a lot of problems using this equation, and we will be continuing our discussion in the next lecture with this.